Hi. Okay, so morning everybody. Thanks very much for coming. We're going to be talking about how we went from zero experience to 60 million player hours using Amazon Web Services with actually a very small team. Just to quickly introduce our company, we work for a company called Frontier. We're based in Cambridge in the UK, and we're an independent video game developer. We've worked with publishers for many, many years, a couple of decades actually, to create PC and console titles. We've done this using our own engine, so very much like an Unreal Engine or Crytek engine, similar performance to that, 64-bit message-based architecture. We use it for all our rendering, and I've got a great tools framework for it. This is a screenshot from a launch title we did for Microsoft for a game called Connectimals, which is a launch title for the Kinect system. And you can see we can achieve AAA quality with it and produce system-selling games. But the real value in having our own technology allows us to innovate in terms of gameplay, because we truly believe that it's the innovative gameplay that is the key to successful games. However, online gameplay experience that we had up until a couple of years ago was literally zero. So we needed to overcome that, and we used a lot of Amazon Web Services help to do that. And of course, we'd also at the same time noticed the opportunity for self-publishing and self-distributing games, particularly on the PC. So taking a step back, where did our company start? In the mid-1980s with a gentleman in the middle there, David Braben, and his colleague Ian Bell wrote a game called Elite, which was a very famous game in its day. It was one of the very first 3D home computer games and the very first what we will now call an open world game. So a game like GTA or Assassin's Creed. This is the very first one. Go anywhere, do anything. And as you can see, you were in a line-drawn universe flying a spaceship round. In fact, it was also the first game to use a technique called procedural generation, and the massive capacity of the computers of the day was the computer it was launched on was a BBC Micro, and it actually had 22 kilobytes of RAM. So that's smaller than most emails we all received this morning. And famously, Elite used literally every bit of that memory to create this amazing galaxy that people were essentially pretending to be Han Solo in, so they were trading, pirating, exploring around this galaxy. So it's a game that we've always wanted to return to, and there were a couple of sequels quite a while ago, and we definitely wanted to return to it in this modern age. So we actually did a Kickstarter. The real purpose of the Kickstarter, yes, money was great. It was the highest Kickstarter ask that was achieved at the time, and certainly that was very useful funding, but we put a lot more than that amount to it ourselves. But it was also actually just to validate the interest from people that were still there for the Elite game, and really importantly to create a community of evangelist players for us during development and through to launch. So move on to our first boss level challenge. Okay, so what we really wanted to do was create a game that had the similar impact to Elite back in the day with today's GPU, CPU technology, and of course, network connectivity. And we want to make a massively multiplayer game. And in fact, Dav, we have a vision for this, okay? And this is the vision that we want to achieve.
First, there was the game client, written in our proprietary Cobra technology. And that's great, but this needs to be a multiplayer experience. So we introduced another game client, and they talk to each other using our in-house UDP protocol. It's a peer-to-peer protocol that's really fast, and it carries all of the moment-to-moment Twitch gameplay traffic. So we have had another game client, and they all establish connections to each other, and they're all talking away. But we need to tell people how they can talk to each other, and when, and indeed who to talk to. So we have a shared game server. We've called it edServer, not hugely imaginative, but there we go. So whenever people connect online, they connect to the game server. The game server watches when they move around the galaxy. When they're about to get within visual range of each other, it tells them to bring up the peer-to-peer connection, they establish it, and then off we go. edServer's pretty fast. We're pretty comfortable with its performance, but sooner or later it gets full. We've got so many players on it, it can't really comfortably support anymore. So we needed to add another edServer, or two, or dozens. So we end up with the risk of having disjoint experiences. This is supposed to be a joined-up galaxy after all. So we introduced a shared layer, a shared galaxy, if it were. And obviously behind every shared galaxy, there's a successful set of shared data services. So we've got DynamoDB, a bit of IDS MySQL, Amazon S3, Redis, we love Redis, Mongo, quite like Mongo too. And we wrap it all together using a PHP API that I'll talk about in some detail a bit later on. And that's all deployed using Amazon's Elastic Beanstalk. But before we get too carried away talking about some of the great tools and technology we've used, we need to take a step back and talk about some basic network services. So when the game clients are talking to our servers, be it edServer or the shared galaxy, latency isn't so much of an issue because it's a server request and we've designed it so that whilst it'd be nice to get it over and done within 50 milliseconds, it's only really a problem if it starts to take seconds rather than dozens of seconds. But the peer-to-peer connections, they carry all of the network traffic of which ship's pointing which direction, who's just fired a laser up who, that sort of thing. So latency is very important there. So we need to provide some services to make sure that people get a really good experience. And so we start off with our game client. And unfortunately, they're behind a firewall, or they might be behind a NAT restrictive router. Yay, NAT, yeah. In order to help with UDP NAT traversal, we provide some basic network relay services. So we've built a package up based on Amazon Minimal Linux, and we use an open source turn server, which provides stan and turn services. I won't talk about them in detail. They're just network basic services. And we host those in various availability zones. But there's no point setting up network relay servers just in one availability zone because latency is sensitive, and if we've got two players in Australia, routing their network traffic via Dublin would perhaps not give them the best experience. So we've set up clusters of these relay servers around the world. So the example here is we've got one in Ireland, we've got one in Australia. We have some others dotted around as well. But we needed a mechanism for distributing players to the closest one to them, and that's closest on the internet, not necessarily closest geographically. So this was where Amazon Route 53 came to the rescue. It's a really simple little system, but it's incredibly powerful, latency-based routing. Whenever one of our network relay services starts up, it registers itself in Route 53. Route 53 knows where that is on the internet, and so when somebody comes along and says, give me a turn server, Route 53 says, yeah, have this one, it's closest to you. But one relay server isn't really going to quite be enough, because sooner or later, we'd exhaust the network throughput of a single EC2. 100 megs gets us a lot of network relay, but we've got a few players as well. So we publish some load metrics up to CloudWatch for each individual cluster of network relay servers. Straightforward CloudWatch alarm. When the alarm gets triggered, scales out another instance. The launch configuration fires up, spawns up a new EC2, user data comes along, bootstraps the process, registers itself with Route 53, starts picking up the load. So that's network relay services out of the way. So the game servers themselves, this is where the money lies. This is really where a lot of the engineering went in. So we'll start off with the core basics, and then we'll build up layers of how we automated this, and we made it into a production environment. So we started off with a EC2 instance. So far, so straightforward. As it happens, we're using C3s, but It's for various reasons. So we have a build on there. In this case, it's EU server number 19. But we needed a way to get the build onto this particular server. So we upload our builds to Amazon S3. Then we have a watchdog script whose job is to sit there watching its bucket and its prefix, saying, well, I need to watch this one. When we say, all right, release this build to this environment, the watchdog comes along, says, all right, take the build, shut down the old server, deploy the new build, start it all back up again. The watchdog also deals with identity. We needed to make sure that our servers had no identity baked into them. They had to pick it up as they go. So they also use EC2 tags. We all like tags, they're great. So that makes calls to the EC2 management API just to go and fetch its tags, go and describe the tags, off they go. However, servers have health, they have loads, they have certain performance characteristics that we're really interested in logging. We're developers, we like logging all of the things all of the time. And sooner or later, we want to set up some rules based on some of those things. So we watch some metrics, take some performance details, and those get published up to Amazon CloudWatch. So the graph that I've shown on the corner of the screen shows the number of players on one particular server instance against the frames per second. It's just a load average, and we can see there's a very clear relationship. Busy server is relatively slow. So one of the really powerful and also quite simple features of CloudWatch is that it lets you aggregate metrics over a whole dimension. So we've got all of the ED servers from the EU cluster all publishing to this EU metric. Then CloudWatch will just let us query a 5-minute moving mean of the average FPS across the entire cluster. When the average FPS gets a bit low, well, we'll trigger an autoscale out, create some more. New servers have no load, so they're really fast. Brings the average back up again, they pick up the load, dips down. It's all really seamless, and it just worked, which was excellent. So these autoscaling rules, they run for a while, and sooner or later we'll get a whole bunch of our game servers running up. Loads and loads of capacity. Then a new player flies along, goes, well, server, please, give me. So this is where the shared API comes in. This is really where the shared galaxy starts to take form. So the part of the shared galaxy API is a session directory. Players hold sessions open on ED servers for various reasons, and this just keeps track of who's where and who's doing what. So this player example here, they're from the United Kingdom, which is on the EU continent, so the EU region would be a best match for them. They've just traveled to the Barnard star system, and the player would quite like to meet other players who are also in that star system. So we look up in our database, see that server EU3, well, that's got most of the players from the Barnard star system on it, so yeah, we'll give you that one. So far, so good. So we have players all over the world in all of the time zones that we found and then some, but the average load, it goes up and it goes down over the course of a day. So it's quite nice to be able to terminate some instances as well as just start them up. And because we really, really can't terminate a server that somebody's busy using, because nobody likes hyperspacing to the main menu, we have to be very careful to drain server connections before we terminate an instance. And that means we need to have really, really fine control over exactly which instance gets terminated and when. It really can't come as a surprise to us. So we made the decision to stack up servers fairly intelligently up to their load capacities. We had an idea about how much load an individual server can support. So the graph I'm about to show you, there's one line for each server instance. This is from earlier on in our beta process last year. So we have several dozen game servers at the moment, and each line just shows us roughly how many players are on there. And then you can see what happened when we switched over our load balancer from just sharing the load evenly. It's great for reliability, but not so great for meeting other players in space. And then we instantly started stacking players up to the capacities, and that gave people a really good matchmaking experience. And it also gave us a much, much easier target for terminating idle servers, which really helps with our load balancing. So, architecture diagrams. We've escaped so far without them, but they're useful, they're great. So, our shared API is written in PHP. It's deployed using the Elastic Beanstalk. So all of the autoscaling magic that just comes with the Beanstalk, it's all there, we're all using it. We might have customized the init script a little bit, but yeah, what can you do? But Because it's an autoscaling group, each individual web server has to be considered disposable. Yes, we use the instance storage quite a lot because it's really fast, but we can't store anything on there long term. If that storage goes away, we can't cry over it. So we have a whole bunch of shared data services for various different data types. So the PHP talks to Amazon S3, talks to DynamoDB, bit of MySQL running in RDS in a multi-availability zone, and Redis, loads and loads of Redis. Redis is great. We also run our own MongoDB cluster. I'll come on to that shortly, because that's not a managed service. We set that one up ourselves using EC2 instances. But running a Galaxy, it's not all about running transactions. Yes, there's an awful lot of single point of truth, so that the API says, yes, you're allowed to do that. No, you're not allowed to do that. But there's also a certain amount of simulation that has to go on behind the scenes just to sync things up and make it a really dynamic Galaxy. So we have a background processor. This shares a lot of the code with the PHP stack, but because its workload is very, very predictable, it just runs on a single EC2 instance off to the side somewhere, has a couple of CPU calls, and it just gets on with it. So it shares the code, it shares the data services, but it doesn't run on the live beanstalk. Now, our game is a cross-platform release. It runs on PC, Mac, and Xbox at the moment, and the API tries really hard to not care about what version of the game client it is. It's just a RESTful HTTPS request. So we have token-based authentication. Every web request comes in, has some headers on it, says, yeah, this is my identity, this is who I am. But because we don't trust our game clients, because people like something for nothing, we have to go and check those claims. So the shared API also talks to external authentication mechanisms, both our own platform and Xbox One. So along the way, we found a number of things that did go as we'd imagined, but there was a few things that took us by surprise, and so we thought we'd share them so it doesn't take you all by surprise. So the first thing was when it came to a straightforward thing, starting up an EC2, terminating an EC2. We know exactly which one's going to close down, right? Well, it turns out not so much. An autoscaling group, it seems really straightforward and simple when you view it through the administration console, but there's actually a whole bunch of worker processes behind the scenes that are working really hard just to keep everything in tip-top condition. And one of those is the availability zone rebalancer. If it turns out that we've terminated loads of instances in availability zone C, then the rebalancer came along, terminated a few in A and B, and sparked up a few more in C, which was a bit inconvenient for the players using it at the time. So whenever we create a new autoscaling group, we make sure we disable that particular background process. And when we terminate an instance, we ask the autoscaler to terminate it for us. That way it doesn't go and start it straight back up again when it notices we're a server down. I mentioned we used EC2 tags for the identity for our game servers. So it turns out that when you have several dozen game servers all polling for tags every few minutes, there's a rate limit on the EC2 API, and you can lock yourself out of your own web admin console. That wasn't so great. So we worked around that one. So we now have a cache of those tags rather than querying them dynamically every time we do it. And we've also engineered it to fail. So if a request times out, we just back off a little bit, wait a couple of seconds. Didn't work? Well, we'll try a few seconds longer. And it's just a lot more forgiving. So therefore, when you lock yourself out of your admin console, mash reload enough times, you get it back in again. We also used PHP's Composer mechanism for all of our dependencies. We have a number of libraries of our own. Those libraries may have dependencies. Those dependencies have dependencies. For ages, we were running Composer at deploy time, which was really great from just a dynamic, agile development experience. But if it turns out that one of those dependencies is on a server that's just gone for a cup of tea, then you can be rolling out instances on the beanstalk, and they're just not working. So we host a cache of our PHP Composer library on Amazon S3, and that turned out to just work really well. It's much faster. We also learned early on that it was great to store orchestration and configuration data in source control. That not only does it save time, so humans are prone to error. We don't like clicking through checklists. It's not fun. We've got computers to do that for us. But it also speeds things up for disaster recovery plans. You do all have disaster recovery plans, I'm assuming. So when you run through them, it's nice to be able to just do a subversion checkout, and there comes your server environment, and there's the code that plays into it, and there's the data that plays into it. Hey presto, instant Galaxy. Yeah, it wasn't that simple, but we got there in the end. So I've mentioned a whole bunch of different data services, but I wanted to mention a little bit about why we had a number of different data services. So we started off with PHP and MySQL, so far so web development, because MySQL, it has ACID transactions. We don't want to risk players' progress. People really like to keep the credits they've earned. They really like to stay alive. So anything that's relational, where we have foreign keys, that all goes into MySQL, and it's really good and high performance. But some of our data, such as how do you describe a starship? What modules have they installed? How many missiles have they got left in their missile pods? That would be quite extensive to describe in MySQL. So we decided that a document store was a much better fit for that. Yes, it's NoSQL, but we use MongoDB. But that meant we needed a MongoDB. So we set up a MongoDB cluster or 2 or 3 or 4 on EC2 instances. So we use C3 nodes. There's 2 reasons for that. The first is they got really good kind of processor efficiency, but they've also got lots of instance storage. And we like instance storage a lot, but obviously we don't store anything we care about on it because that leads to disappointment. So at the moment we're using just a single EBS volume, general purpose, so bursty I/O. And for a while, we were struggling with I/O throughput. We didn't want to go down the provisioned IOPS route unless we really, really had to. But turns out that MongoDB 3.0 came along. It just hit release quality just in time for us to use it. And it has a new storage engine in it called Wired Tiger. And that has built-in compression, which really, really cut down on the amount of IOPS we were pushing out. And that meant that the bursty nature of general-purpose SSD was perfect for us. We found that the MongoDB replica sets, they just worked out of the box. Set them up, off they go. Replication, multi-master, choosing elections, it all just works until the primary dies. And then we're left with 3 availability zones, and now we're down to 2. And then we've got 2 servers having a vote. They both voted for each other, and you get 2 primaries. And then nobody wants that. So thankfully, MongoDB thought of that one. And so there are, as an arbiter instance, it runs on a T1 micro, runs nothing but Mongo. It's got no data storage in it. And all it does is it helps out with elections, just so there's always an odd number. It's really vital when you're running any sort of database cluster or in fact, any sort of cluster. We've tried a number of different backup strategies. And the one that's worked for us is to have an actual secondary node that takes all of the replication traffic and stays completely up to date, but it's marked as hidden in the replica set, which means it never actually serves any production traffic. So what that means is that it's always up to date until it comes to be backup time. Then we simply switch off Mongo and back up from one EBS volume to another, so there's no I/O contention. That gives us a nice flat file that we can just upload to Amazon S3, start up Mongo again, the op log plays back in, and that's then back up to date, ready for later on. We did have to experiment a little bit with the instance sizes that we used for the various Mongo nodes, because as our players wax and wane, so did our databases. And rather than just adding lots of replica sets and taking them away, we discovered it's better to scale up and back down again individual instances. But rather than breaking apart and rebuilding the replica set every time, we found it was really useful to set up some well-known names, and then we'll just change the IP addresses of those. So again, root 53 and internal, it just gave well-known names to keep replication working fine. One final note on Mongo. We had to be a little bit careful with the way that we set up our PHP code to be really careful for watching for timeouts. So if we've got a distributed transaction where somebody spends some credits to buy a ship, we don't want one half the transaction to work and the other to fail, and the player to be left with neither credits nor ship. So we had to be careful to always roll back into the player's favor. Had to spend a little bit of time engineering for that.
So, good job, Smarty Pants. So here we have a multiplayer game. Well done. So what we really want to do is kind of set this game in a real one-to-one sized Milky Way galaxy, because we want to really differentiate ourselves, and there's no point having kind of random made-up galaxy. I want to be real. I want to be compelled. I want to be able to fly into the galactic core and see nothing but stars around me. I want to see everything orbiting in a majestic cosmic ballet. Majestic cosmic ballet, okay? And I've got a vision for that, you'll be pleased to hear. This is some time-lapse photography from one of our players took in the game. So you can see the majestic cosmic ballet in action, which is good news. So the good news, Dav, is that I actually know a little bit about galactic formation. And I know everyone else here knows this, but just to recap a bit of galactic formation 101. So we all know that galaxies are formed from interstellar gases, that there's basically slight ripples in terms of density and features start to form, and then microscopic kind of grains of sand start to clump together, and then gravity acts on these things such that they start orbiting and colliding and whirling around each other. You eventually get to a situation where all this is happening, and the young stellar object at the start of this or the center of all this stuff is so large, it starts to self-compress and ignites in nuclear fusion, resulting solar winds blow away all the non-bound gases, and you can see the kind of shadows there are shadows from planetary objects. And then obviously millions of years pass with all these things orbiting around each other, colliding, sticking together in some cases, and so on. And also, the other good news is that we know that there are about 160,000 observable stars from Earth, so we can have all those for free from all the different star catalogues, and also we can sample the mass density of the galaxy as we know it, and also what we know of the chemical composition of the galaxy. So it should be pretty easy. So over to you.
So, thankfully, there were a great number of very clever developers back on our team back in Cambridge, and some of them have a great background in theoretical physics, maths, and so on. So, what we've got on screen here now is a visualization in Excel from our StellarForge simulation. This is it's a consistent simulation that gives us a one-to-one scale model of the galaxy. And this was a screenshot taken during some early prototyping. It gave us really quick feedback and let us iterate quite quickly. And it was showing us that we're getting not just stars, but we had moons, we had ring systems. It was giving us binary star systems all the way through the galaxy. But this wasn't just, oh, you've got a star here and a moon here. It was a really, really in-depth scientific simulation of the chemical composition of that. So it also gave us things like, how big is it? What's the surface temperature? What's the atmosphere of that moon? How often are we likely to get volcanoes? How deep is the sea going to be? We've got a really good set of data to draw upon if we actually need to. And whilst Excel is all very well and good for the design team, it's perhaps not so great for the end gamers. So this is what it looks like when it's rendered in our system view, which we were really quite happy with. So this gives us a one-to-one scale view of the galaxy. But players like to go and do things in that galaxy. And before we do that, we need to talk a little bit about why we use different data stores. I'll come on to this in a little bit. Building blocks, we'll use the building blocks. So I mentioned EC2 SSD storage quite a bit so far, and we like it a lot because it's really fast. It's not on the end of an Ethernet connection. It's as close to our virtual CPU as we're ever going to get. So we use that to hold on to copies of data that are not likely to change and are not likely to be different between individual web servers in that cluster. When we need a fast cache of things that have to be consistent, so things that can change, we fall back on Elasticache Redis as a straightforward caching mechanism. We also use Redis's structured data services, but we'll come on to that later on. MySQL and Mongo, I've already talked about. For data that changes very, very rarely, but we read quite often, that's a great choice for Amazon S3, where eventual consistency is absolutely just fine with us. And finally, when we want something to be really, really consistent, we ask our simulation code. That will always give us the same answer every time, but it costs us a certain amount of CPU, so it's an act of last resort. Even MySQL acts as a cache for StellarForge with the number of rows in the database table. One of the key tenets for keeping everything really fast and responsive was we're only going to store interesting data. Now, this seems a little bit simple, but to us, something is interesting when a player has interacted with it, whether it's player progression, nobody likes risking player progression, or it's been changed away from its default state. And I'll come on to that default state because it's quite important to the way that we've run our galaxy.
Yeah, sorry. Yeah. Is that better? Better? Yes. Okay. So we have our massive multiplayer game. We're now set in a one-to-one representation of the Milky Way galaxy. Clearly, I want my players to be able to do something in that galaxy. I want them to be able to kind of explore, find new star systems that have never been discovered before. I want them to get credit for that discovery in the game, both in terms of actually in-game credits and their name in lights in the game as well. I want them to be able to go between different star systems and trade things between different star systems, perhaps yes, buying food cheap in one place, taking it to another place, selling it for a profit, and so on. And I want this to be a dynamic market. I want a galactic-wide commodity market simulation. So I want every trade that every player does to affect the price of the commodity that they're trading. And obviously I want them to be able to do something with that as well. I want them to be out to be able to upgrade their ship, better engines, better weapons, new pirate paint job if they want, for example, or indeed new ships, new fleets of ships.
So, exploration, the data set that just keeps on growing. So, well, I've mentioned that we've got 400 billion star systems, and we've got an ever-increasing number of players that go flying around space. So we need to keep track of which star systems have they been to, what have they discovered, have they done a detailed discovery scan of the atmosphere of the third moon of Endor. There's any number of combinations that give us just a data set that is going to grow to the square of, well, the square, but the multiplication of the number of star systems and the number of commanders. But we can be fairly confident about the number of reads and writes to that data set because that's dependent on the number of players currently online right at that very second. And so it's a perfect fit for DynamoDB. Means that we can take a reasonably straightforward document, that's just a list of bodies, and we've got just who it is, who owns it, and we put it into DynamoDB, and it takes care of the storage scaling for us. We did originally do this in Mongo, and yes, it got us to release day, but eventually the scalability got too much, and it was time to use Dynamo properly. For commanders that were lucky enough to go and discover to go and scan a body or a star and then bring it back to civilized space and sell it, they get credited with first discovery bonus, which means that their commander name is forever written in lights in the galaxy. And for that, we use Amazon S3. Somebody only ever gets first discovery tags once when they do the selling, and then when somebody else goes and visits that star system, they just read what's already there. So written once, read it back, S3, perfect. Another building block that we use is transactions. We haven't really talked about kind of data streams, data flow, and our game is no exception. So when somebody comes along and performs a game action, kills an NPC, takes some profit from a trade, blasts a chunk off an asteroid for mining, any one of those actions can generate a number of individual game events in our log. And because the individual transaction doesn't care about the consequences of that, we queue it up in Amazon SQS for dealing with later. We just need to get that over and done with. So that goes into the queue. Then a background process is watching that particular queue, and then dispatches those into one of our MongoDB clusters for later analysis. MongoDB, as well as just being a pure document store, it also has a really powerful aggregations engine, which lets us say, I don't know, let's have a look at trade. So we start off with our core simulation. So we know using our generation systems exactly how much stock is available in any given market at any given point in time. But that just gives us a default. And players want to change those defaults so that they can have interesting things happen. So the way that we dealt with this, again, this is interesting data. So we start off with 1,000. One player comes along and buys 200 units of fish. And then another player comes along and says, how much fish have you got? They need to see 800. But rather than storing a database cell with 800 in it, we actually store that as a multiplier of 0.8. So we take the default values and just start putting modifiers on top of it. Then over time, the background simulation comes along, restocks it a bit. It might be a water world that's got high nitrogen atmosphere or whatever, and that means that fish get regenerated really quickly. And sooner or later, the stock levels return to their defaults. But rather than storing a multiplier of 1, we delete it completely, and it all relaxes back to its default state. And this is how that works behind the scenes. So I mentioned that all transactions end up in our MongoDB cluster. The background processor comes along every few minutes and says, give me a summary of everything that people have bought and sold at all the different markets around the galaxy. And then MongoDB goes away, runs the aggregation, comes back with a list of, well, we've bought and sold all of these things. The supply and demand simulation takes the modifiers that are currently there, runs it through the mill, and comes out with a bunch of new modifiers, and those get stored for everybody else to come along and query. And that gives us nearly real-time supply and demand mechanics that meant we didn't need to run a finance system the size of the galaxy. So we also use those data for trade routes. So we know where everything spawns in the galaxy, but a player is just looking at a single view of it. So we need to help people buy and sell. So we have trade routes in the game. And again, this is a background process, runs once a day or so, and it looks at who's bought stuff and sold it where, who made a profit. Okay, well, they've done that, so we'll add that as a trade route. And you can imagine exactly how complicated this network looks when you have this many markets and this many commodities and this many players buying and selling things. Analytics. We all like analytics. We like to be able to see what's going on behind the scenes, and we use a product called Kibana. I'm not going to dwell too much on it, but we use it for just looking at health checks. Just by staring at the shape of something over time, you get a feel for whether it's happy or not. It's a really great tool for drilling down into dimensions and summarizing data that is very much self-service. Rather than pestering the development team for, can you just run us a report on this? We need to answer this question. It's a self-service tool that helps our support, QA, design, and even the development teams themselves. Kibana also lets us build statistical distributions, and I won't go into probability theory here, it's okay, but it lets us see what are people generally doing, and it also lets us spot outliers when somebody's doing something that wasn't quite within the design parameters. And the way that this works is based on the same principle. We have the transaction logs that I've already mentioned. Those are going into SQS. And this time we have a different set of queue dispatchers, and those watch a different queue, and those dispatch those into an on-premise Elasticsearch cluster that we run. And then we have Kibana running against it, a couple of versions of that. We have some custom reports, and it's really fast, really real-time, and it just keeps roughly up to date with all the various logs.
So that's pretty cool. Just to break out of the pointy-haired manager persona for a second, this is exactly how we actually developed and rolled out our game, because it was an early access game on PC. We actually, the development mirrored the risks as we perceived them. So our top risk actually wasn't any of the networking or the galaxy or anything like that. It was how the ships felt to fly, because that's what people do on a second-by-second basis in the game. So our very first release was the flight model of the game. Second release, all the networking, multiplayer stuff. Third release, all the Galaxy trade routes, etc., started building up, and over time we increased the number of users on our servers from, I think, initially about 3,000, the very first build, through to about 200,000. Our pre-release, literally our pre-release final tuning build had about 200,000 people working on it. So back into pointy-haired manager mode. So we've got this fantastic Galaxy that's interactive. People could do lots of things in it. It's cool, but although I do know that open world games are traditionally very difficult to tell stories in. I really, really want to tell a story in this Galaxy, but I want it to be a very player-driven story. So as well as blazing their own trail like Han Solo through all this stuff, I want them to be able to work together and the aggregate of what they do to actually influence the fate of star systems. So if there's perhaps put it into civil war, and we could perhaps change the control of who is controlling that at the moment. Also, I want community goals. So I want something that perhaps every week that our players could all band together and do to achieve something to change the state of the Galaxy. And perhaps even people want to oppose that as well, which they'd be welcome to do. And finally, I really want a kind of cinematic experience. I want players are understanding what the overarching story in a very cinematic way is, and perhaps be able to influence the main players in that story and what those players' strategies and next moves are. Okay?
Absolutely. So I've talked a little bit so far about how players have their own actions and how they progress an individual commander, but we need to start bringing this together into a dynamic Galaxy, and this is where the political simulations come into play. So again, transaction logs. This time, so whenever a player goes, they might have assassinated a pirate lord, or they might have made loads of profit selling fish to this mining colony, or they might be evil. They might be going out committing acts of piracy around the Galaxy. Each of those actions has to have consequences for the political minor factions that are affected by that. Either they were the victim, or they were the person who benefited from that mission. So every player action starts to add changes to what we termed buckets, which are stored in MongoDB. So here we might have advanced 1 point along the state towards an economic boom, or somebody might have lost a certain amount of influence in a star system. Influence is kind of important. So that gives us these buckets that are stored in Mongo. And those are one per faction, so there's not very many, it's about 100,000, something like that. And then our background processor comes along, and this runs every day, and it reads in. This is kind of a summary of all the player actions from a faction point of view rather than the player point of view. It then runs through the simulation and decides what the new value should be. So it might say, well, you've made loads and loads of profit, so you go into a state of economic boom. So prices come down, stock levels go up, it's all happy times. Or it might be that the pirate faction has gained so much influence in that star system, it can challenge the current owners of that star system for control of it, and then a conflict might spawn, at which point the game servers pick up on this. We start little conflict zones spawn in the Galaxy, players come along, they start shooting the people of the side they want to oppose, and influence changes, and sooner or later a winner gets declared, and to the winner go the spoils of victory, and that can sometimes flip control of the star system. So if somebody wants to support the rule of empire or kick the empire out and make it an independent freedom system, then that will happen, and the simulation just takes care of it. Taking that to the next level, we needed ways of focusing players on certain activities because when players all arrive in the same area of space, you often get some emergent gameplay, both from people trying to do this action and from people trying to oppose that action. And you get some really exciting stories that happen. So for that, we use community goals. And the example here is pushing the Emperor's Dawn out of one particular star system. So from a fundamental point of view, it's players doing an awfully large amount of a single quantity of a single action. And for that, we use MySQL again. Because players have to have progression, we can't risk that progression, so we needed to use transactions for that. But rather than melting holes in many, many database cells with all those rights, because we don't have so many community goals active at any point in time, and players generally hand in batches of an action, it generally works out all right. But we also needed to have leaderboards. So the person who did the most to kick the Emperor's Dawn out gets many, many more rewards for their efforts than someone who just rocked up at the last minute and said, yeah, me too. So for that, we use Redis. So leaderboards, real-time leaderboards. That can be a bit of a pinch point, especially when the data are being stored in MySQL. But we double enter the data into Redis. Redis has a feature called sorted sets. I'm not going to go into it in a huge amount of detail, but we already had this data structure available. We just used it. Real-time leaderboards, no extra charge. If Redis goes away for whatever reason, like it runs out of memory, we restart it, bring up a new node, then the leaderboard is automatically rebuilt, either from the state of MySQL or from a snapshot that we've left in Amazon S3. Taking that to the next level once again, we have PowerPlay, which is one of our major releases earlier on this year. Now, this is where players support one of 10 powers in the galaxy for a fight of dominion and control of space. And this is a really, really powerful game. It really does give you concerted actions, players vying for control. So, no, I want to expand into there. No, I'm going to oppose you expanding into there. It's really big. And again, because player progress is involved, we had to use MySQL for this. But in order to make it fair, we couldn't make this a real-time simulation because we needed to give people a consistent playing field for that week. Because some people might only be able to play at certain times of the week, they may only be able to play at weekends, or they can only play every Tuesday evening. So rather than trying to make this a real-time simulation, there's a weekly turn that runs as part of our weekly maintenance cycle. It takes about 20 minutes every Thursday morning.
Okay, so super cool. So going back to the start of the presentation, you remember that we are kind of self-publishing this game on PC. So we want an online store and a mechanism to distribute it to our players. And over time, we obviously want to sell extra products and obviously other games that we do over time as well. So can we have that as well?
Yes, we can. So the Frontier platform. So this is also running using the Elastic Beanstalk. It's written in PHP, and we use a number of open source frameworks such as Drupal and Magento. It's stored using a MySQL shared instance, and this hosts our various online storefronts. We have a number of them integrated with various payment gateways. It's all relatively straightforward e-commerce. So a player comes along, buys the game, and downloads the launcher. The launcher is actually downloaded from S3. We sign them a URL just for them. They download the launcher that's specific for them, and they log into it on their computer. The launcher then connects to our authentication servers, which are also a Beanstalk, different Beanstalk, but sharing the same database. And that tells us which products that particular user has authorized for that session. So the launcher then gets a list of products that they're entitled to. It might be the production game, that might be one of our beta backers from Kickstarter, and they might be entitled to get to use the test servers as well. So I mentioned many, many minutes ago that the game builds were stored in Amazon S3, and the same goes for the actual client builds that they get. We have a manifest-based system, so people, for small patches, only need to download just the files that have changed, rather than the full game client every time. And that's distributed around the world using Amazon CloudFront, so that we're not blocked by S3's outward-bound bandwidth. It gives people a really consistent download experience, especially if they're not the first person to have downloaded it since we released a certain patch. Once the game client's downloaded, off they go into space. Doesn't quite end there from the point of view of the platform and authentication mechanisms, because the game servers themselves also check back with the platform login servers to find out is this person entitled to this product? Were they one of our Kickstarter backers and are entitled to one of the various reward tiers for that? Had they purchased some extra content, such as some paint jobs, to really customize their own vessel? We check and police that behind the scenes to verify people's claims.
Okay, cool. So at this point, I'm getting quite happy. So we've got a multiplayer game that we're distributing online off our own website and doing really, really well. And then I'm sort of looking at different audiences for this, try to expand the audience. So I'm looking at different distribution channels. So it would be awesome to have it on Steam, for example, still on PC and Mac, and also different platforms as well, as in game platforms. Love to have it on Xbox because we've got a great history with Xbox, and so we've integrated both those distribution and e-commerce channels with our servers. And as we're going on to console as well, this is a very rewards a long playtime, the Elite Dangerous. There's a lot in there, and we have a very, very high average play time for our players. And so for a console audience, what we'd really like to do is add a mode of gameplay where we allow instant action, player versus play action, a bit like kind of Call of Duty lobbies where you can just get in and start fighting with people. And I have a vision for what we want to do with that.
The Federation welcomes you to CQC, Closed Quarter Combat Championship.
The games. Every pilot has a reason to compete. Find your fame. Test your mettle. Hone your skills. Become a champion.
So, CQC, our instant action player versus player game, which launched this week. So, for platforms that support native matchmaking, such as Xbox, we use that. But for platforms that don't, PC, we had to build our own. And we needed a way of grouping people together. Some people might want to play with their friends, some people might be on their own. So we needed to group people into lobbies, and from lobbies into game sessions. And for that, we needed to leverage all of our existing services to support that. So, build a matchmaker, they said. How hard could it be? So, using our PHP shared API and a feature in Redis, we built our very own matchmaker. So the key here is Redis has a feature which is a blocking list pop. Doesn't sound very exciting, but it means you get a lightweight, fast, reliable queue for no extra charge. It's all part of Elasticache. Then our background processor comes along, see who's queued up, who has said, I want to sit in this queue, I want to go and work in I want to play team deathmatch, or I want to play capture the flag. Comes along, checks who's waiting, checks all of the various background matchmaking mechanisms, I won't drill down on that here, and groups people up into lobbies and said, right, you look like a game, have a go. And that then runs along, and then many, many thousands of people have been through it.
Yeah, super cool. So the one were their seasons. So way back right at the start of our development on Kickstarter, we said to people that we're going to be doing this game, but we're going to be continuing to evolve it. And some of the major expansions of the game would be paid for. So I want a way of being able to essentially do seasons like a sort of kind of AAA TV series like Game of Thrones or something like that. I want that kind of seasonality. And in fact, I can feel the second season of this coming on. And I want that to be we've got this Stellar Forge which simulates the galaxy, but how about allowing our players to land on every planet in the galaxy? And we want something to do for them down there, so we want them to basically extend all the gameplay that they can do in space down onto the planet surface so they can explore, fight with each other, trade things, or find things to trade. There should be fortifications on the planet surfaces for them to do. They should be able to work in conjunction between ships. They should be able to drive around the surface of the planets in vehicles if they want, leave their spaceships behind. Then perhaps they want to start, later on in the season, they want to start playing with other players in multi-crew, being able to see what each other's players look like, so player characters in there, crafting loot-based systems, lots and lots of fantastic things. We'll need an in-game marketplace as well for less frictional in-game purchases as well. And I've got a vision for that, which I'd like to share with you, Dav, if I may. So what do you reckon?
That many star systems, that many planets, we're going to need some more servers.
Okay, thank you very much, guys.
Thank you, everybody.